So yesterday we were discussing about 3-bit asynchronous counter, 3-bit asynchronous up counter. So it's working. We were discussing, and we were at the state when output of your counter was 1, 1, and 0. So let us see what happens. If we apply clock pulse, if your previous state is 1, 1, and 0, and now suppose if I have applied a clock pulse here. So after application of the clock pulse, the flip-flop number 1 is going to toggle, and it will toggle from 0 to 1. Okay, and as this output transition is applied to the clock of flip-flop number 2, it is experiencing 0 to 1 transition, so it will not be triggered, and therefore output state of flip-flop number 2 will remain the same, which is equal to 1. And as output of flip-flop number 2 is not making any transition, which is applied as a clock to flip-flop number 3, flip-flop number 3 will also not make any transition, so it will remain same. So now the new output is 1, 1, and 1. So after 1, 1, 0, the count which is counted by your counter is 1, 1, 1. Now let us see what happens after application of one more clock pulse. Now suppose if we are applying one more clock pulse here, what changes now going to occur, that we are going to see here. So after application of the clock pulse, as you can see, the first flip-flop is going to toggle. So it is going to change the state from 1 to 0. So as it is changing state from 1 to 0, this is a trailing edge of the clock pulse, and this trailing edge of the clock pulse is applied to flip-flop number 2. So now flip-flop number 2 is experiencing trailing edge of the clock pulse, that is changed from 1 to 0, and therefore flip-flop 2 will also toggle. It will change the state, and it is changing the state again from 1 to 0. So flip-flop 2 is also making transition from 1 to 0, and this is applied as a clock to the third flip-flop. So now your third flip-flop is also experiencing a trailing edge of the clock pulse, and therefore this is also going to toggle, and it is going to change the state. It will change its output from 1 to 0. So now our new output is 0, 0, 0. So after 1, 1, 1, the flip-flop will be resetted to the state 0, 0, 0. Okay, so this is how the 3-bit asynchronous up counter will work. Now, two things we want to do is we have to draw the truth table of this flip-flop. And from this truth table, we have to draw the waveform, which is also called as a timing diagram of the counter. So these two things we are going to do here. Okay. So are you clear about the working of the counter? Please respond in the chat box. Yes, respond in the chat box. Shall we move ahead? Shall we write the truth table and timing diagram of the counter? Shall we move ahead? You write in the chat box so that I'll come to know. Yes? Okay, I will write truth table here, and how to draw timing diagram from truth table, that also I am going to show you how to do it. Okay, so you can listen to me, isn't it? Can you listen to me? Am I audible? Okay, let us draw truth table. Clock and outputs Q2, Q1 and Q0. So here you can see when we apply during your zeroth state, the output was 0, 0, 0. The state counted was 0th state. Okay. Thereafter, we have applied the first clock pulse, and here we have obtained the output at 001, and this is called as state number 1. For second clock pulse, we will have 010, which is state number 2. For third, 011, this is state number 3. For fourth, 100, this is state number 4. For fifth, 101, this is your state number 5. And for sixth, it will be 110, which is your state number 6. For seventh clock pulse, it will be 111, which is your seventh count. And after this, after 7, again for eighth clock pulse, you are going to have 0th state back. So this is how we can write the truth table of this counter, 3-bit up counter. So this is up counting starting from 0, going to 1, 2, 3, 4, 5, 6, 7 and back to 0. So this counting is done in increasing order, and therefore this is called as up counter. Now we must be able to draw the timing diagram from this truth table. Okay, so first we will have to draw the clock pulses here. So there must be 7 states. So what I will do is I will wipe out this state column, and here I'm going to add one more clock. Okay. Let us draw clock. So each time we have to consider the trailing edge of the clock pulse, where the transition is going from 1 to 0. Okay. So let us see whether we have 7 trailing edge clock pulses. Yes, there are 7. Okay. So for the 0th clock pulse, here what you have to do is you have to write Q0, then Q1, and then Q2. Now here, as you can see, Q0 is making transition on every negative going clock pulse. So initially Q0 was 0. During your first clock pulse, it has become 1, and thereafter it has become 0, again 1, again 0, again 1, again 0, and again 1. Okay, so these transitions you have to see. So this must happen at trailing edge of the clock pulse. So this is a waveform of Q0 because it is continuously making transition 0, 1, 0, 1, 0, 1, 0, 1. So this is a waveform for Q0. Now, if you observe Q1, then you can observe for 2 clock pulses it is 0. For 2 more clock pulses it is 1. Again for 2 clock pulses it is 0. And again for 2 clock pulses it is 1. So this is what we have to draw in the timing diagram. So initially for 2 clock pulses it is 0. Thereafter it is making transition 1. So for 2 clock pulses again it will be 1. So again it is making transition becoming 0. For 2 clock pulses it is 0. Again for 2 clock pulses it is 1. So it will be 0, 0, 1, 1, 0, 0 and 1, 1. So that is what you can write. Now we are going to write about or draw waveform of Q2. So now if you observe Q2, for 4 clock pulses it is 0, and thereafter for 4 clock pulses it is 1. And again after 4 clock pulses it is making a transition. So it takes 4 clock pulses to make a transition. So that is what we have to draw here. So here for 4 clock pulses it is 0, and for remaining 4 clock pulses it is 1. Okay, so 0, 0, 0, 0 and 1, 1, 1, 1. So this is how we are going to draw what is called as waveform or timing diagram. So these timing diagrams are very important in case of counters. So here you can observe the count. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And after this, it will become 0, 0, 0. Even you can extend this diagram. Okay. So you yourself try to draw this truth table and diagram. Okay. So are you clear about this? Write in the chat box. Take a screenshot of this, or you can draw along with me in your notebook. Okay. So are you clear about this? Write in the chat box. Write in the chat box. Are you clear about this? Yes, write quickly so that we can move ahead. Yes or no? Type in the chat box. Okay. So I think you have taken a screenshot. You have taken a screenshot, all of you. Okay. So now what we will be doing is we are going to verify the working of the down counter, 3-bit down counter. Okay. So I will wipe this diagram and I'm going to draw the logic diagram for 3-bit asynchronous down counter. Okay. As this is 3-bit counter, you need 3 JK flip-flops in toggle mode. So let us draw 3 flip-flops, JK flip-flops. So all these must be connected in toggle mode. So for that connection is connect J and K together and connect it to plus VCC or logic 1. So this is what is conversion of JK flip-flop and into a toggle flip-flop. So in counter, JK flip-flop is used as a toggle flip-flop. You remember always this. And thereafter what we have to do is we have to apply a clock pulse to the first flip-flop. And after that, the change in the connection of up counter to the down counter is that instead of connecting Q0 to clock, you have to connect Q0 bar to the clock of the next flip-flop. So here connect Q1 bar to the clock of the next flip-flop. So in up counter, what we did, we have connected Q0 to clock, Q1 to clock. Okay. But instead here we are connecting Q0 bar to the clock of next flip-flop and Q1 bar to the clock of next flip-flop. So this is the change we have to make if we are converting the circuit from up counter to down counter. Okay. Now here you can observe this is your Q bar. And this is Q1 you can say, and this is Q2 you can say. This is your LSB and this is your MSB. Okay. So as 3 bits are there, 2 to the power of 3, this type of counter is going to count 8 states. 2 to the power 3 is equal to 8. It is capable of counting 8 states, and as it is a down counter, it is going to count in the decreasing order. Suppose if we start from 1 1 1, if this is your initial state, then your next state will be 1 1 0. Now suppose if you are starting from 0, that is suppose if your flip flop counter is in reset condition, that is output of each flip flop is 0 0 0, then the next state will not be 0 0 1, instead it will be 1 1 1. So this is the basic difference. So when making a transition from one state to another state, the down counter will go from 0th state to 7th state. So 1 1 1 is its first state, as you can say. So let us verify it's working. Okay, so we will consider output as 0 0 0. Let us consider the initial output. Initial output of your counter is 0 0 0. Okay. So if this is the case, and if you apply the first clock pulse here, then what will happen? So the first flip-flop is going to toggle. So first flip-flop is going to toggle, and it is going to toggle from 0 to 1. It is going to toggle from 0 to 1. And as it is going to toggle from 0 to 1, as the inverter is present here, so second flip-flop is also going to toggle from 0 to 1. And similarly, the third flip-flop is also going to toggle from 0 to 1. So now the next state will be 1 1 1. Okay. So after 0 0 0, the next state will be 1 1 1. Okay, so after 111, suppose if you are going to apply the second clock pulse, if you are going to apply the second clock pulse, then this flip-flop is going to change the state from 1 to 0. And as it is making a transition from 1 to 0, the flip-flop 1 will not change its state, it will remain in the same state. So it will be 1. Similarly, as this is not making any transition, so output of third flip-flop will also remain the same, which is 1, 1, 0. So we have to start from MSB and then go to LSB. So the output that we are getting here, it was 111, here it is 110. Now suppose if we apply the third clock pulse, then what will happen? So let me write it here. So after applying the third clock pulse, what will happen? This 0, 1 and 1, it is going to change. 0 will change to 1. Okay, so this will change to 0 and this will remain the same, that is 101. So your next count will be 101. So like this, go on applying the clock pulse and you will be getting the output which is in the decreasing order. Okay, so output will be in decreasing order. So we should be able to write a truth table of this, and we should be able to write the timing diagram for this. Okay, so now working of the 3-bit asynchronous down counter is very similar to 3-bit asynchronous up counter. Only the difference is the clock is connected to the complemented output and not to the direct output. So this is the only difference that you can see. So here now I am going to write the truth table. So let us write the truth table. So clock, state and output. Q0, Q2, Q1 and Q0. Okay. So 1, 0, 1, 2, 3, 4, 5, 6, 7 and 8. 0, 1, 2, 3, 4, 5, 6, 7 and 8. So here you are going to no, after this 0, 7, 6, 5, 4, 3, 2, 1 and again 0. So this will be 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1 and 0, 0, 0, and after this 0, 0, 0, again there will be 1, 1, 1. So 7. It is like this. So this is the way in which the truth table of the down counter can be drawn. Okay, so that is what you can observe over here. So now I am going to draw timing diagram from this truth table. Okay, just like previous timing diagram. So drawing a timing diagram is very important in case of counters. So let us draw the timing diagram for down counter. First we will draw clock pulses and then we are going to draw the outputs. 1, 2, 3, 4, 5, 6, and 7. So these are the clock pulses. After this, I have to draw Q0. Q0 is making transition from 0 to 1, 1 to 0, 0 to 1. It is changing for every clock pulse. So that is what you have to remember. Q1. If you see Q1, for one clock pulse, it is 0. For next clock pulse, it is 1, and it will remain 1 for 2 more clock pulses. Thereafter, it will remain 0 for 2 more clock pulses. It will remain 1 for 2 more clock pulses, and again 0 for 2 more clock pulses. So it is the way in which we have to draw Q1. And for Q2, you can observe initially it is 0, and for 4 clock pulses, it will be 1. And thereafter, for 4 clock pulses, it will be 0. So let us write the states here. 0, 1, 0, 1, 0, 1, 0, 1. And here 0, 1, 1, 0, 0, 1, 1, and 0. So here 0, 1, 1, 1, 1, 0, 0, 0. Okay. So if you see the counts in this timing diagram, it starts from 0, 0, 0. It will go to 1, 1, 1, then 1, 1, 0, 1, 0, 1. This is down counting. 1, 0, 0, 0, 1, 1, 0, 1, 0. And here it will be 1, sorry, 0, 0, 1. Correct. 0, 0, 1. So it is correct. And after that, it will be 1, 1, 1 again. Okay. So you can extend this timing diagram yourself. So are you clear about this truth table and timing diagram? Are you? Type in the chat box. Type in the chat box. If you draw it yourself, you will understand whether you are getting or not. Try to do it yourself. Okay. So now we'll be moving to next type of counter, which is called as bidirectional counter. Okay. So I'm going to draw the circuit diagram of bidirectional counter here. So this type of logic or this type of circuit can count both in forward as well as in reverse direction. Okay. So let us draw the diagram for such type of counter. Okay. So I'm going to draw it. So it is called as 3-bit asynchronous up-down counter. 3-bit asynchronous up-down counter. Okay, so this is also using 3 flip-flops. It is able to count 8 states, but in both directions. So we have to use additional logic for that. Okay, so first let us draw flip-flops. We are going to use JK flip-flop in toggle mode. Always remember this. All these need to be connected to logic 1. So this is Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar. Okay. So here we need additional circuitry. here we are using 2 AND gates. There is very less space. 2 AND gates and 1 OR gate. Okay, 1 OR gate. And output of OR gate is applied to the clock. Okay, Q0 will be applied as one of the input to the AND gate number 1. Q0 bar is applied as one of the input to AND gate number 2. Outputs of AND gate number 1 and AND gate number 2 are acting as inputs of OR gate. Okay, so here similarly here we have to draw 2 AND gates and 1 OR gate. Even you can draw this configuration with NAND. This will be easy to understand, therefore I am showing this to you. Okay, so here this is up control line and this is down control line, and this is clock. This is what your circuit is. Okay, so in addition with 3 JK flip-flops, we are using here additional logic using and OR gate for up and down counting. Okay, so for this reason, what we have to see how this circuit works as up counter and how it works as down counter. Okay, so that is what we have to see. So for up counting, your up line must be at logic 1 and your down line must be at logic 0. Okay, so let us see whether this works or not. So if up line is at logic 1 and down line is at logic 0, then